The human heart has the ability to beat independently without any nervous input. This is because it has something called a cardiac conduction system. This begins with the pacemaker. The pacemaker keeps the pace of the heart. Without any input from the nervous system, the heart will beat about 72 beats per minute. So this is made possible by electrical impulses that travel throughout the heart and making the heart beat synchronously. So let's go over these. The first step is the pacemaker. The pacemaker is otherwise known as the SA node, and from there the information goes to the AV node or the atrioventricular node, and then to the AV bundle, followed by the bundle branches, number 4. Number 5 are the Purkinje fibers. Let's go over these again. So first we have the pacemaker, which is the sinoatrial node, otherwise known as the SA node for short. This is very important because if something is wrong with the SA node, then the entire heartbeat will be irregular. So next we have the AV node, number 2, which is the atrioventricular node, followed by the AV bundle, which is number 3. And then we have the bundle branches that take the information to the ventricles and all through the heart via the Purkinje fibers, which is number 5. Altogether, we call this the cardiac conduction system. If there are any irregularities in the cardiac conduction system, it will be seen on the ECG, producing irregular and unusual heartbeats. In order to understand the electrical impulses that are generated at the SA node, we need to understand how action potentials are generated at the SA node. So we call this a nodal action potential. Here's the graph. The x-axis we have time in seconds, and in the y-axis we have membrane voltage in millivolts. Let's make a few important points. Minus 60 millivolts, minus 40 millivolts, 0 millivolts, and plus 30 millivolts. The minus 40 millivolts is important because it is the threshold voltage. If you remember, the threshold voltage is the minimum voltage needed to trigger an action potential. At minus 60 millivolts, voltage-gated sodium channels open and sodium flows in, causing a depolarization. At minus 40, voltage-gated calcium channels open, and at plus 30, voltage-gated potassium channels open, producing an action potential. From minus 60 to minus 40, we call it the pacemaker potential. This is in the place of a resting membrane potential, which the heart does not have. It has a pacemaker potential in the SA node. So the action potential has a depolarization phase and a repolarization phase. The depolarization phase is caused by calcium and the repolarization phase is caused by potassium. So let's review this. The pacemaker potential is caused by slow sodium inflow, depolarization by fast calcium inflow, and repolarization by fast potassium outflow. Together we have an action potential. Let's review what we just learned about the formation of an electrical impulse at the SA node. The first stage is the formation of the pacemaker potential. At minus 60 millivolts, voltage-gated sodium channels open and sodium flows in. So there is an inflow of sodium. So let's repeat that. At minus 60 millivolts, voltage-gated sodium channels open. There is a slow sodium inflow. Sodium inflow brings in positive charges, and so there is a slow depolarization. The voltage now reaches minus 40 millivolts. The range of voltage between minus 60 millivolts and minus 40 millivolts is called the pacemaker potential. Remember, this is different from the resting membrane potential in the neuron because the SA node does not have a resting membrane potential. It never rests. It only keeps the pace. So we have a pacemaker potential. The next phase is the depolarization phase of the action potential. This is brought about by the threshold voltage. We remember that the threshold voltage is the minimum voltage needed to trigger an action potential. So at minus 40 millivolts, voltage-gated calcium channels open. Fast calcium inflow occurs because if you remember, there is more calcium outside the cell, so there is always a calcium inflow. Calcium inflow brings in positive charges, so this causes a depolarization, a rapid depolarization that makes the voltage go up all the way to plus 30 millivolts. So from minus 40 millivolts to plus 30 millivolts, we call it the depolarization phase of the action potential. It is the rising phase when the voltage increases. The third phase is the repolarization phase of the action potential. This is brought about by the opening of potassium channels. Potassium channels usually open around 0 millivolts. In this case, the depolarization is so fast that it passes the 0 millivolts and reaches plus 30 very rapidly. So around plus 30 millivolts, potassium channels open. These are voltage-gated potassium channels, and this causes potassium to leave the cell. Remember, there is always more potassium inside the SA node cells, so potassium leaves the cell. So we have a fast potassium outflow. This causes positive charges to leave the cell, resulting in a repolarization, and this repolarization is also rapid and reaches minus 60 millivolts so that the cycle can now repeat. The voltage from plus 30 millivolts to minus 60 millivolts, we call that the repolarization phase of the action potential. So far, we have seen the SA node under normal conditions. The top graph here shows two action potentials within a given time frame. In the same time frame, on the bottom left, we see that there can be three action potentials. On the bottom right, it is extremely slow with a slow pacemaker potential and only one action potential within the same time frame. The top graph is the normal condition. The one on the left is under sympathetic stimulation, and the one on the right is under parasympathetic stimulation. Whenever you exercise, your heart rate goes up. This is because the sympathetic nervous system is turned on and it acts on the SA node, causing it to raise the heart rate. So let's see how that happens. Here we have sympathetic stimulation of the SA node. This causes the permeability of the calcium and sodium channels to go up. So the permeability, meaning the calcium and sodium channels open more, and so this increases the movement of sodium and calcium. Therefore, there is fast inflow of calcium and sodium. Even though sodium is normally slow, it's a little bit faster. And this increases the rate of depolarization. So there are faster depolarizations within the same time frame. So we end up with more action potentials within the same time frame. So the number of action potentials goes up. So if that goes up, the heartbeats per minute goes up as well. So number of beats per minute goes up. So that's the arrow going up, meaning it increases. And so the heart rate increases. Again, we use the arrow going up. So here we have it. Sympathetic stimulation of the SA node results in an increased heart rate. When a person is suffering from an anxiety attack, they have a very high heart rate. This is sometimes addressed by prescribing beta blockers, which have the ability to lower the heart rate. What a beta blocker does is to block the adrenaline receptors on the SA node. If you remember, adrenaline has something to do with the sympathetic nervous system. So it blocks essentially the action of the sympathetic nervous system on the SA node or our pacemaker. So the beta blocker, here we have it, results in blocking adrenaline receptors on the SA node. Now adrenaline cannot bind to its receptor because it has been blocked by the beta blocker. Sympathetic stimulation of the SA node goes down. So we're going to use a down arrow to indicate decrease. This results in the permeability of the calcium and sodium channels to also decrease. So we will use the down arrow to indicate decrease. As a result, there is slow inflow of both calcium and sodium. Now, if there is slow inflow, there's going to be slow depolarization. So slow depolarizations occur. When this happens, you're going to have fewer action potentials in the same time frame. Fewer action potentials per minute. Fewer action potentials at the SA node mean fewer heartbeats per minute, resulting in a lowered heart rate. So there we have it. Beta blockers resulting in a low heart rate. The term arrhythmia means irregular heart rate. This can come in two forms: bradycardia, which means a slower than normal heart rate, or tachycardia, which is faster than normal heart rate. People with tachycardia are often prescribed calcium channel blockers that will lower the heart rate and bring it back to normal. So let's take a look at how calcium channel blockers lower the heart rate. Calcium channel blockers lower the permeability of calcium. So the calcium permeability decreases. We see the down arrow for decrease. This causes calcium inflow to slow down. The slow calcium inflow causes the depolarization to slow down as well. When the depolarizations are slow, we have fewer action potentials per minute. Fewer action potentials means fewer heartbeats. So we will have fewer heartbeats per minute, resulting in a lowered heart rate. Now this is beneficial because the heart rate is going back to normal. So there we have it, a calcium channel blocker resulting in lowered heart rate.